Hello and welcome to Lecture 4. This week we're moving on to forces. This lecture we're going to spend some time introducing the concept of forces and a tool called free body diagrams. We'll go over what we learned in the reading about Newton's 3 laws. We'll recap all of the types of forces that we'll see in our problem solving. And then we'll spend some time using these tools to investigate the type of problems you'll be expected to solve. In physics, when we say force, we are trying to describe a quantity that's going to help us understand how objects interact with each other. In nearly all of the concepts that we investigate later in the course, forces will play a key factor. In their most simple consideration, forces can be considered as a push or a pull that influence motion in their direction. No matter the type of force, whether it's a push or a pull, they will be considered as a vector, and as such, they will have a direction and a magnitude that we will measure in newtons. This unit, the newton, represented with a capital N, is the amount of force required to accelerate 1 kilogram at 1 meter per second squared. This means we can convert newtons by thinking them as 1 newton is equal to 1 kilogram multiplied by meters per second squared. If you want to get an idea for what a newton feels like, you can find some change in your house. And if you happen to have 23 quarters or 14 toonies, if you hold that in your hand, that is exerting 1 newton of force on your hand. If you don't have that much change lying around, and you happen to have a scale that's accurate down to the gram, you're looking to hold on to a mass of 101 grams, and that will tell you what 1 newton feels like. I want to share with you a little bit more contextual understanding. In the universe, we can look at forces as being one of 4 fundamental categories. The first of the fundamental categories is gravitational forces. Gravitational forces describe the attraction force between any 2 or more bodies with mass. The second of the 4 fundamental force categories is the electromagnetic force. These are the attractive and repulsive forces between charged particles. As we get talking about the types of forces we will deal with, many of them are electromagnetic. The next type of fundamental force is the weak nuclear force. The weak nuclear force is responsible for the decay of atoms into other atoms. And the strong nuclear force is responsible for keeping subatomic particles like quarks near each other. As we move from left to right through those 4 forces, it is likely that you would have less and less reason to experience or understand or work with the category. And currently, in leading-edge physics studies, theoretical physicists are trying to describe and define a theory of forces that would unite these 4 fundamental forces. Before moving on, we need to make sure that everybody understands a tool that we will use to set up and visualize force problems. We need to look at the rules for drawing free body diagrams. Free body diagrams always start with a body, and that body could be in 1, 2, or 3 dimensions. And your drawing needs to include an positive axis. Because you get to choose which way is positive in your problem, it's very important to communicate that choice to your readers. This is simply done with a compass rose. So you can see here a axes defining positive x, positive y, and positive z. While many of our studies in physics will use right-hand rules for the axes, you must be aware that it's possible to have a setup with a left-hand rule, which would have z pointing the other direction for positive. And the last thing we do is sketch on our vectors to represent our forces we are interested in. There's some rules we need to follow when sketching our vectors. First, we only draw on forces that act on this particular body. We represent forces as arrows in the direction of the force leaving the box. So we see vectors going right, left, down, up, into the page, and out of the page. Note that sometimes the convention used to describe into and out of the page will look like a circle with an X, which would represent an arrow going away from you. The X shows you that you see the tail of the arrow. And a vector coming out of the page would be a circle with a dot trying to represent that you are looking at the point of the arrow coming towards you. And while we are considering these as sketches, not scale drawings, the length of the arrow should be proportional to the magnitude of the force. With all of this information on our sketch, free body diagrams will help us to identify whether there's a net force in any particular direction. Now let's move on to talk about how we understand forces. We're going to focus on Newton's 3 laws of forces. Unfortunately, it's a common situation that our everyday observations of forces lead us astray to the true nature of how forces interact. We have to pay close attention to these 3 laws. In a very brief summary of the 3 laws, Newton's first law tells us that motion is changed by forces. Newton's second law helps us to calculate and predict the amount of change that forces will cause. And Newton's third law helps us to understand all forces interacting on separate objects. Now we'll look at each of the 3 laws in more detail. You've read about the first law in your textbook. You've seen the official definition of the law and a translation of it. And I want to provide another interpretation. Without a net force, objects at rest will stay at rest, and objects in motion will stay in motion. As your textbook pointed out, it is rare for us to see any object without a force operating on it. This means that it's really rare to see an object without a net force acting on it. But I need to emphasize this point several different ways. In complete absence of a net force, there will be no acceleration that the object experiences. Our difficulty here is that we often see that an object with a velocity will slow down eventually. And we assume that that object has no net force. The reality is that the object that's moving will have an unseen force of friction working on it, which means that there is a force acting and pulling the object slower. To understand how much the object's motion will change, we need to use Newton's second law. Newton's first law told us that a net force will change an object's motion. Newton's second law helps us to understand how much it will change the motion by. So Newton's second law gives us the sum of all the vector forces acting on an object is equal to the mass times the vector acceleration of the object. Let's make sure we are clear on what all of these variables are. So the large Greek character here represents sum, so it means to add up everything. And because it's attached to the F with a vector overhead, it's saying summation of vector forces. Because these are vectors, it means we will have to do this summation based on the components of each vector. The F here is representing all of the forces acting on the body. So we can see that a free body diagram helps us get an image of which forces we need to be considering when we go to do the calculations using Newton's second law. The M represents the mass of the object, and we'll talk a little bit more about this in a couple of slides, but the mass is the measure of a body's ability to resist a change in motion. It's really important to recognize that our net forces influence acceleration, so the change in velocity. This fact leads to some of those conceptual misunderstandings that we've experienced in our previous chapters. You will experience some questions on the assignment that try to expose this misunderstanding. Take a second to consider the nature of the relationship between these quantities. Force and acceleration are directly related, so more force means more acceleration. Similarly, the more mass you have means the more force you need to create the same acceleration. And think of that more mass will mean less acceleration. So mass and acceleration are inversely related. All of these details will become useful when we move on to solving problems that involve forces. Newton's third law, the action-reaction pairs. To every action, there is an equal and opposite reaction. This again gives us an equation we can use, and this equation is one of those equations that we use to help us set up problems. So again, let's examine how our notation works here. So we have two vector forces, which means direction matters. And we're using our notation here to say the force from A acting on B. And when we flip the subscript notation to have BA, we're considering the force from B acting on A. You will likely have experience with this. Think of a time where you've had to try and push something heavy across the ground. You apply a force on the box. The box applies a reaction force against you. And in some of those situations, the reaction force is enough that you slide away from the heavy object. The other part of this equation is telling us that the direction changes, but the magnitude of these forces stays the same. The book gives you the example to explain these reaction forces as gravity, pointing out that you exert some gravity on Earth and Earth exerts some gravity on you. These forces are equal and opposite. And again, we lead to a misconception that we aren't doing anything to Earth. But the reason for this is that the mass of the two objects is so vastly different. Remember, if you have more mass, the same force causes less acceleration. So while the Earth is able to force us to accelerate, we have very little ability to have the same reaction on Earth. We have a conceptual difficulty here. Careful consideration of action-reaction pairs must be made. It's important to note that action-reaction pairs act on different bodies. So both forces in the pair cannot be drawn on the same free body diagram. The force that A applies to B, so the force that you apply to the Earth, would be drawn on the free body diagram for the Earth, and the force that the Earth applies on you, or the force that B applies on A, would be drawn on the free body diagram representing you. You must keep this in mind anytime you're asked to identify action-reaction pairs. Now that we understand the laws that govern forces, we need to move on to considering the different types of forces that we'll encounter. Depending on the type of force we are looking at, there's different ways for students to misunderstand the concept. To give you an idea of what's coming, let's quickly sketch a free body diagram. So we'll take a block, and to make things slightly more interesting, we're going to rotate that block a little bit, and we're going to have that block sitting on a surface. So all objects will have some force that pulls straight down on them, and we typically represent that force with a W with a vector arrow on top. If we take and apply a force to our object, we can draw that applied force in the direction that that force is applied, and we'll often see a force that works in the opposite direction of motion, pointing the opposite way. Now, because this object is just a quick sketch, I haven't considered the size of each of these vector forces. We're just getting an idea of all the different applications that could show up. As we said at the start, the most general interpretation of forces is that they are either a push or a pull. In this case, we're going to think about forces that we apply directly to the object. So if we consider our box, and we consider somebody coming along and applying a push to that box, then the most common force we see is an applied push. When we sketch this free body diagram, we don't need to include the little stick figure, but there is a common mistake that occurs. Vectors representing pushes must be drawn leaving the object. So the correct vector in this situation would come out of the far side of the object and be represented as our force applied. Students often incorrectly look at this and say, if I'm pushing the object, then my force must look like this. And this would be an incorrect way of representing on our free body diagram. The other application direction of force is pulling forces. So again, we have an object and we have a person, and they have a rope that they're using to pull on our object. These types of applied forces have a special consideration. Forces pulling an object through a rope, wire, or cable are considered as tension forces. So our pulling forces include tension, gravity, and magnets. As drawn, we would be considering the object and its source as a system, but sometimes we can consider the object and the source as separate pieces, and in those situations, a push force would increase the distance between the object and the source, and a pull force would decrease the distance between the object and the source. We need to look a little bit more closely at tension. In our consideration of tension forces, we make the assumption that ropes, chains, and wires do not stretch. While this is unrealistic, it helps us to have more static problems that will be easier to solve. The other assumption we make is that ropes, chains, and wires do not have mass. Again, while this is unrealistic, it allows us to complete our calculations without increasing the mathematical difficulty of the problems. You should note here that all of our applied forces are drawn in as vectors. And you have to consider that an applied force that is at an angle will act in two planes. So on here, while we drew the force of tension as being horizontal, often we'll see that as you pull on an object, you pull up a little bit. Similarly, that while we showed the force applied as a push as being horizontal, often what happens is you even push down a little bit on the box as you push. If your force is said to be applied to the box, you can assume horizontal until you're told an angle. Whether or not they're a push or a pull, we often think of the applied force as the motivating force behind any motion, and then begin to consider all the other forces that apply to calculate the net force. One of the other special pull forces that we talked about was gravity. When we talk about the force due to gravity, in physics we give it a special word, weight. Because we are considering weight as a force, it is measured in newtons. This is one of the areas of physics where you're essentially learning a new language. Your everyday usage of the word weight is incorrect for the application in physics. When you step on a scale and get a value in pounds or kilograms, you do not weigh that much, you have that mass. Scales are essentially conversion tools that convert the force of gravity that you're applying to it into a reading of the amount of mass you have. The other thing to try to keep straight in your head is that the force due to gravity is not interchangeable with the acceleration due to gravity. Remember from projectile motion that the acceleration due to gravity is represented as g with an arrow over top and is 9.80 meters per second squared down. Whereas the concept we're talking about here, the force due to gravity, is represented as the weight, w with an arrow over top, and can be calculated as mass times acceleration due to gravity. Weight points straight down. So the direction of this vector will be that the gravity acts on the center of mass of the object and always points towards the center of Earth. So this calculation is set up to tell us the amount of force the mass of Earth exerts on the mass of our body. And to calculate that, we will need to have the mass of the body and the acceleration due to gravity near Earth. So again, we have a common misconception here. Even though the body is stationary, G still applies. Whenever we have a stationary body, so we have an object sitting on a surface, that object still has a weight. So even though it's not possible for this object to move downwards, we still use that acceleration due to gravity to calculate the magnitude of that weight. You have to work really hard to get over your habit of saying, I weigh so many kilograms. Your mass, measured in kilograms or pounds, will stay constant no matter where you are in the universe. But your weight, referring to the force due to gravity, will change based on which planetary body you are close. So your mass on Earth is the same as your mass on the moon. But because the Earth is so much larger, the acceleration due to gravity is 9.80 meters per second on Earth, and it's something like 1.62 meters per second squared on the moon. So while your mass is the same in both locations, your weight will be vastly different. The next type of force we look at is the normal force. To try and help you keep straight in your head what the normal force represents, I like to think that the normal force keeps your world, well, normal. This is the force that exists so that you don't just pass straight through your chair, and your laptop's not just going to pass straight through your desk. You can feel in your backside that the chair is pushing up on you a little bit, and that is you feeling the normal force the chair exerts on you. So again, let's consider where the normal force applies. We'll draw an object on a surface. Because this object is in contact with the surface, it has a normal force. And we represent the normal force with an F and a subscript capital N. The normal force is purely reactionary, which is a way of saying that the normal force will change in magnitude to ensure that there is no net force between the object and the surface. So with no other applied forces, the normal force would be equal and opposite to the weight. However, in a more dynamic situation, where we start with a weight and a normal force, the normal force and the weight are equal and opposite. But if we begin to apply a tension force, note that the normal force will shrink as we apply more. Again, the normal force will only exist enough to ensure that there is no net force perpendicular to the surface. The normal force will always act perpendicular to the surface. There was one last type of force that we listed on our previous free body diagram. When two objects are touching, there's a force acting between them other than the normal force. This is the force due to friction. So we have a formula we use to calculate the magnitude of the force due to friction. You'll notice that this formula does not have vector arrows. We will need to interpret the direction of our force, as right now with our level of math, we can only calculate the magnitude. In this formula, you'll see a new variable. Mu represents the coefficient of friction. It is often a decimal number that essentially scales the amount of force applied. We have two types of friction we consider. Static, which we use a subscript S, and we use static friction anytime the two surfaces are stationary relative to each other. As soon as the two surfaces start to move relative to each other, we consider that a kinetic situation. So we apply kinetic friction whenever two surfaces move relative to each other. Generally speaking, a mu value, a coefficient of friction for static surfaces, is going to be greater than the coefficient of friction for two surfaces that are kinetic or moving between each other. From the equation, you'll see that the force of friction depends on the amount of normal force. So if we have more normal force applied, then we will have more friction. If we have less normal force applied, then the friction will decrease. As I said, our equation is focused only on the magnitude, and we will have to interpret the direction. That direction will always oppose motion. Generally, static friction resists letting body begin to slide, and kinetic friction is constantly trying to slow a moving body down. There's one last type of force that we need to talk about. We're going to talk about the forces that apply to springs. Our understanding of spring forces are defined by Hooke's law, and Hooke's law can be represented with this equation. The force of a spring is equal to the negative of the spring constant multiplied by the displacement from equilibrium. Spring forces are thought of as restorative forces, which means they react to how far they've been stretched away from their equilibrium point. So if we consider a spring with an equilibrium point, if we compress that spring, meaning that we push on it to shrink the distance of the spring, as we push in on that spring, the force tries to push back against us to bring the spring back to its equilibrium point. Similarly, if we were to pull on the spring and stretch it out, then this force the spring is applying would be trying to pull the spring back into the equilibrium point. For our equation, you can see that we are looking at the magnitude, but this negative sign also helps us determine which direction it's going to be. This force is very dynamic, so the more we pull, or the farther we've stretched the spring, the more force we experience. Because of that, we will often just do static calculations. So what is the force on the spring to stretch it to a specific position? Earlier when we talked about tension forces, we mentioned that we think of wires, strings, and cables as not stretching. If they did, we would have to consider them as if they were a spring. For any given material, the spring constant changes. And while we won't consider this property, each material has a limit to how far it can be displaced before Hooke's law no longer applies, as in we've broken the material and it will not try to return to its equilibrium point. Now that we understand all the types of forces that we can interact with, let's attempt to create a free body diagram. Consider a block with a mass of 220 kilograms on a ramp that is angled at 35 degrees. If you can exert a force of 1,130 newtons attempting to pull the block up the ramp, and that block has experienced a force of friction equal to 636 newtons, also up the ramp. Draw the free body diagram. So we need to label all of these forces. So we have a ramp. That ramp makes an angle of 35 degrees. On the ramp is a block. We've been told that the block has a mass and that we are applying a tension force and that there's also a frictional force. And when we start to think about these problems, we need to consider that if there's a mass, then we know there's a weight. The weight will point directly towards the center of Earth, which means it doesn't point perpendicular to the ramp. So we'll draw it straight down on our diagram. And if the block is on the ramp, then the block will also be experiencing a normal force that is perpendicular to the ramp. At this point, we are done our free body diagram. We've labeled all of the forces that we know of, and we've drawn them with vectors roughly proportional to the size of their force. Note that it is an option for you to label the mass inside the block. You do not always need to do this. Whether we're working in 1, 2, or 3 dimensions, force problems generally take the same approach. Problems will have a force component and a motion component, and our job, as always, will be to determine what we know and what we need to know, and then use the information given and our understanding of the concepts to solve for the missing information. One of our most powerful tools to accomplish this is the equation that came with Newton's second law. This is again an equation, so it follows our similar rules. If we know any 2 quantities, we could find the third. So as it is, if we know the mass and acceleration of the object, we can calculate the net force required to cause that motion. But with rearrangement, if we know the force applied and the acceleration, then we can reverse engineer the mass of the object. And yet another type of problem is that if we know the force applied and the mass of the object, we can determine the acceleration effect. The fact that the acceleration and forces are both vectors means that we have to consider them in their components. This means that we could have a net force in the x direction while having no net force in the y direction. When it comes to solving problems that involve forces, there is a major common misunderstanding. You must keep in mind that constant velocity means no net force. This is not the same statement as saying constant velocity means no force. When we are solving situations, we are using our knowledge of the forces that are applied to determine the acceleration of the object. We can then take the acceleration of the object to go on and solve a kinematics problem similar to the ones we saw in lectures 2 and 3. Let's look at solving a few examples now. Let's look at our strategy to employ when we are asked to find what force is required for constant velocity. Consider a plane with the following forces applying. So again, it's important to consider all the information available to you. Most students will be able to pick up that they were given 2 forces, but another very important piece of information here is that our plane is moving at a constant velocity, which means we also know that the acceleration is equal to 0. So if we're required to find force number 3, our approach should be that if acceleration is equal to 0, then net force is equal to 0. And remember, we need to work in each component separately. So let's break our problem into 2 parts. We need to think of the x direction and the y direction. Overall, we know that the sum of all of the x components will be equal to 0. So we have 0 is equal to force 1's x component plus force 2's x component plus force 3's x component. This is the piece we don't know, so we need to rearrange the equation. So force 3 x component will be equal to negative force 1's x component subtract force 2's x component. And we have the same system on the y directions. As always, I encourage you to find formulas to replace the x and y components and calculate once. So if we focus on force 2, we can see that the x component will be equal to force 2 times the cosine of theta 2. We have equations like that for all 4 of our known components, so we can substitute them now. Now for each of these directions, I don't have any unknown values, so I can start to substitute. The magnitude of force 1 is 200 newtons, but if we look at our diagram, the angle 270 degrees, starting from the horizontal, goes all the way around and points straight down. The cosine of 270 degrees is 0, so this entire term cancels out, which means we only have negative 150 newtons from force 2 times the cosine of 200 degrees. Now looking at the y direction, again there's a special consideration for the angle that we have, 270 degrees. The sine of 270 degrees is just negative 1. So in that case, we will have a negative 1 from sine theta. So we'll have negative magnitude of F1. So we get 200 newtons. And our consideration of the angle is already complete. So then we add 150 newtons and sine of 200 degrees. We're going to take a second and look at how these calculations break down, just so you see where the signs come from in our final answer. I don't expect you to complete this step. So we have a negative value, and the calculation we get from 150 times the cosine of 200 gives us a value of negative 140.9538931, which means we end up having a positive x component to force number 3. Now, if you've chosen to substitute values and complete your calculation at this stage, keep in mind we're not done. We need to go to polar notation, which means we still have calculations to complete later. So if you've done this, you need to look at your calculator and use the store feature. So on the Sharp calculator, it's an STO button, and then you can store the value into any of the 5 letters on the row that has all its exponent keys. When I do this, I use the notation of writing whatever letter I used to store and circling it. So that means I've told my calculator to keep this value and all its decimal places in the A memory bank. And if you've completed the calculation on the Y components, you would have 251.3030215 newtons. And again, because I'm going to need this value, I will store it in the B memory bank. So these are our X and Y components of force number 3. And now would be a good time to confirm for yourself, do I expect a positive X and a positive Y? And if we look at force 3, we're moving right for the x coordinate and up for the y coordinate. So yes, I expect these values to be positive. And as you saw from that quick sketch of the components, we expect the y value to be greater. Now let's work on completing the last step, converting to polar notation. So in this case, when we're looking for the angle, we're looking for theta. And we know we calculate that from tan inverse of force 3's y component divided by force 3's x component. And I should be more specific that this is theta for force 3. Similarly, when we're looking for the polar magnitude, we would be looking for the size of force 3, and we would use force 3's x component squared plus force 3's y component squared, and we would need to take the square root of that value. So at this point in time, we have to substitute our values we've already calculated and stored in the memory banks, but we would have been better served to come to this portion of the problem at this step in the equation and input those equations into these places. That means we could let our calculator do one calculation and solve this all at once. Because we have very few significant digits in this problem, it's going to be okay to work with the stored memory banks. So to use the memory banks in your calculator, you're looking for the RCL button, and you just go back to the same letter you stored the value in. So we have our Y component stored in the B memory bank, and we want to divide that by the X component, which is stored in the A memory bank. So when we plug these values into our calculator tells us that this is 60.712 and a whole bunch more information degrees. And we'll just answer to the whole degree here. So we have approximately 61 degrees. On the magnitude side, we again would just recall the values that we want. So this is the memory bank A. Make sure that it gets squared, added to the memory bank B, which also needs to be squared. And we need to take the square root of that entire statement. And our calculator should tell us 288.134. We don't need any more information than that. Newtons, which is approximately 288 newtons. So the third force required for constant velocity would be approximately 288 newtons at an angle of 61 degrees. So because this vehicle has constant velocity, we would assume that it already has some V value, so it is moving, and it's applied just enough force to maintain that velocity. If we had any increase in force number 2, then that would begin to have a net force applied, and the vehicle would slow down and descend. Similarly, if there were any increase in force 3, then there would be a net force in that direction, and the vehicle would actually be accelerating or ascending because of the directions of force 3. The second problem we're going to look at asks us to describe the motion of the block we used in our free body diagram example. So let's pull up our free body diagram. And if you recall, we were told that the force of tension had a magnitude of 1,130 newtons, and the force of friction had a magnitude of 636 newtons. We weren't given any other forces, but we were given the mass of the block as 220 kilograms. If we have the mass, we can calculate the weight. So the magnitude of the weight force is going to be calculated using m times g, which gives us a magnitude of 2,156 newtons. I approach all of this in the setup phase because our weight calculations are generally fairly straightforward. Our normal force calculations, though, are actually slightly difficult. If we're asked to find the motion or describe the motion of the object, this is the problem's way of saying that you are required to find acceleration. So our approach is going to be to find the net force. There's a very powerful strategy here you should apply. You can choose the X and Y directions. And often we just see students choose Y to be straight up and X to be directly to the right. But in problems like these, that means that you're going to have to decompose the force of tension into X and Y, the force of friction into X and Y, and the force normal into X and Y. And the only force that is actually directly in your coordinate plane is W. So if we take our coordinates and decide to turn them so that they're in the same direction as our ramp, then now force normal is entirely in the Y direction, force tension is entirely in the X direction, force friction is entirely in the X direction, and the force weight is the only one we need to decompose. So because you can choose the direction of X and Y, set ramp problems with X and Y in the direction of the ramp. When you do this, it means we have to do a little bit of thinking of how we break down our weight vector. So we're going to have a component in the new Y direction that is perpendicular to the surface of the ramp, and we'll have a component that's in the new X direction, which is in the same direction as the ramp. When you turn the ramp, the angle between the actual direction of the weight vector and its Y component will be theta. But note, you cannot just use our typical formulas for breaking this into x and y, as our x component is now opposite of our angle, and our y component is adjacent to our angle. So you have to be able to set these angles up and their sine and cosine functions based on this new arrangement. So with all that information on our diagram, I'm going to shrink it down a little bit and work at the calculations. Again, we need to work in the x and y directions separately. So in this case, we're looking for the net force, which means we're looking for the x component of that net force, and we need to add the force of tension's x component, the force of friction's x component, and the force of weight x component. Because of our strategic setup, we know that the force of tension is entirely in the x, the force of friction is entirely in the x, and the force of weight, if we look at our triangle again, the x component is the far side, so we're going to be looking at the weight magnitude multiplied by the sine, and here if we look, we measure back to positive x, so positive x is this direction, and this angle is not quite 270 degrees, so we subtract from it 35 degrees, so we have an angle of 235 degrees. So we know we have values for all of those variables, so let's switch our focus to the y direction. Again, we're looking for the net force, and that's going to be the force normal's component in the y direction, and it's going to be the force of weight's component in the y direction. And again, because of our strategic setup, we know that the force normal is entirely in the y direction, and the force of weight magnitude times the cosine of 235 degrees will represent the y component. Now we need to take a second and look at our diagram again. As we look at our x component, this refers to if the block is moving up or down along the ramp. The way most ramp problems work is that we assume the block is sitting on the ramp and does not leave it. So because the normal force is entirely a reactionary force, we can make the assumption that our force normal is equal to and opposite direction of the force weight's y component. So what this tells us is that in our y direction, there is no net force. We only get to make this blanket statement that there's no net force because of our adjustment to the x and y directions. If we left x and y as they were, then the total component of the force normal would match the component of the weight that is perpendicular to the surface, so the block wouldn't suddenly fly away, but the calculation would be much more difficult. I'm going to revert to my standard approach for solving these problems where we substitute equations, not values, and now we're going to move on to the portion of the problem where we attempt to solve for the motion. Because we know that our entire net force will be in the x direction, that means that we do not have to consider the y direction anymore. But when we're describing motion, we need to use the equation F net, the sum of all of our forces, is equal to mass times acceleration. We're after acceleration here, so we can rearrange to say that acceleration is equal to F net divided by mass, and we can substitute what we know. F net is equal to the force of tension plus the force of friction plus the weight multiplied by the sine of 235. And we'll divide this entire thing by the mass. So we can substitute our values. We have 1,130 newtons from tension. We have 636 newtons from friction. We have 2,156 newtons from weight, but we only want a component of it based on the sine of 235 degrees. And we have a mass of 220 kilograms. Now, if we plug all of this into our calculator, we get negative 0.000417306. And we can do some work to look at our units, and if we have newtons plus newtons times by, remember that when you take the sine of an angle, you actually have no units left. So the top is all newtons, and we're going to divide by kilograms. So looking at our dimensions, we have newtons divided by kilograms, which at first glance doesn't seem to make a lot of sense. But remember, the newton is a kilogram meter per second squared. So that means we are going to cancel out our kilograms and kilograms, and we're only left with meters per second squared, which is good because those are our units of acceleration. But that number may still seem odd to you. So let's go back and break down what happens in this calculation. If we look, we have two values for newtons that we actually know. So if we add those together, that's 1,766 newtons. And I'm going to calculate the third force component there, 2,156 times the sine of 235 degrees. And you'll see that that value becomes negative 1,766.09 and a bunch more information, newtons. Remember, if you're looking at this angle, we have positive x here, we have 235 degrees here, which means the component of our weight in the x direction is negative. Obviously, our weight vector was not drawn to an appropriate scale here, but it does help us see that there's a lot of force pulling down the ramp to offset that large tension and friction force that we had. One thing that's important to mention here is that when we look at problems next week where we're asked to determine the force of friction, it may have been difficult for students to recognize friction would be pointing up here. So one of the things to think of is friction is a reactionary force. It tries to oppose first motion beginning and then motion continuing. So if we look at this situation with an acceleration very nearly zero, we could say that this object has constant velocity. Because friction always opposes the direction of motion, we can infer that this box is trying to move downhill, which makes sense because the box has a very large component in that direction from its mass, and the tension itself is not enough to offset that weight. So the friction here is actually helping the person stop the box from sliding down the ramp. The only thing we have left to do to complete the problem is to round to say that this is 0 meters per second squared. And our statement says that the box would have a constant velocity, and because of the direction of the force of friction, we can't really say for certain that the box is at rest, but we know that it is either at rest or sliding down the ramp. This week was mostly about introducing forces. Next week we'll look at solving more difficult problems. But before then, I want you to consider this plane, and I want you to tell me if this plane is about to fall out of the sky. You'll need to base your judgment on the fact that this plane has a thrust equal to 35 kilonewtons, a lift equal to 7.84 times 10 to the 4 newtons, a weight with magnitude 7.84 times 10 to the 4 newtons, and a drag equal to 35 kilonewtons. The concepts we introduced today will help you understand this problem. To date, we've just been using our formula at the bottom of our quizzes. At this point, I'm going to introduce you to your formula sheet. The front side of the formula sheet will have the formula you've already seen, plus the new ones we introduced this week. You are permitted to have this formula sheet with you for all 3 tests and every quiz. It's important that you print a copy off and have it available to you while you're practicing your questions, and that you have a clean copy with no writing on it available to you for your quizzes. As the semester goes on, we'll introduce formula sheets 2 and 3 as we get through our topics that we will use on tests 2 and 3. Note that our formula sheets will be cumulative, which means you will be allowed to use formula sheet 1 for all 3 tests. You'll be allowed to use formula sheet 2 for tests 2 and 3, and you'll be allowed to use formula sheet 3 for test 3. Each week that a formula sheet is introduced, you're allowed to use it starting that week on the quiz. Not pictured here is the conversion that we mentioned in class, which will be on the back side of the sheet, so it's important that you're able to print double-sided. Again, recapping this lecture, we introduced forces. We focused on using Newton's 3 laws to define our understanding. We also talked about many different types of forces we consider applying. We introduced the free body diagram, which is a method to help us visualize all the forces acting on an object. And we tried to take a systematic approach to solving force problems. We looked at just 2 types of problems: given all the forces, describe the motion, or given information about the motion, describe all the forces. Next week, we will start to add more dynamic problems where we determine how the body moves after a force applied or while a force is applied. This material will be on your quiz this week, so be sure you've prepared. And this will also be the last new material that goes on test number 1. And if you have any questions, feel free to email your professor.